Rafael will show a professor from Brazil will show his cheap invention for motor control. Yeah. So please start.
Yes. Just a minute. I also want to show a video. It's quick. Sorry for the delay. Okay. So this is the platform I mentioned. We are working with students using this platform as a way to get they engaged and started in Verilog design quickly. Our proposal is that these guys can easier and quicker get engaged and then get interested to learn more. Okay, so this is the platform I mentioned. It's called Chip Inventor, and you can drag and drop blocks. And you can create your own blocks. So we created an encoder block, 1 Hertz clock, pulse counter, the bouncer, and as we connect those blocks to input pins of quadrature encoder and some pins, some push buttons to define set point, a reference angle, we can implement a kind of simple closed loop control system with a UART interface to plot in real time the angle of the motor axis. Okay, we are talking about a mechanical motor, people, a mechanical DC motor with a quadrature encoder that measures its position. So we have a desired value here as a start and a gain, and this all is added together and computed so we can use a demux. So we use basic digital logics concepts here to control the intensity. We may have a PWM somewhere here so that we can switch on and off the two output pins that goes to a driver, an L298 age bridge driver to the DC motor, and if the desired position is higher than the measured, then it spins anti-clockwise, otherwise it spins clockwise. I want to show, it's real quick, this video. Should download this, just a minute. I think it will be, okay. Movie could not be found. This is an unexpected. So I'll show on my smartphone, and maybe I can send you guys later. Just a minute. It will be real quick. I want to show the system working. It's with a Tang Nano 9K, okay, guys? So it's affordable. As you just have to get a Tang Nano 9K and a DC motor, and here it is. So you can see like a tire, a wheel. I turn it by my hand, and it always gets back to the desired position using that diagram I just showed you. And that diagram will generate a Verilog file. I'll show. Okay, this is the demo working, and what we have done, we work with beginner users can do that. As we use these blocks, each block will generate a Verilog module, the mux, adder, the bouncer, and We have a top module here that integrates all these modules, and we get what I just showed, okay? So it's a Tang Nano 9K, and this, I don't know if anyone is interested, but if anyone is interested, I can show each DC motor encoder. It's this one. Maybe where can we? This one. You can buy it on AliExpress, of course. And it's in Brazilian reais here, but I can change it to US dollar. Let's see. But it's like $6. You have a gear, a reduction, mechanical reduction. You have the quadrature encoder here, and you need an H bridge. But you can build a very reliable control system using this approach. And what is very nice is that you can multiply these to 3, 4, 5 motors. That is not possible with a microcontroller, in my humble opinion. Like you can put 10 DC motors here and control them all simultaneously without one interfering in other. Okay, Yuri, I don't know if you guys could hear me well.
Yeah, we can hear you. Yeah. Mm-hmm.
Okay. So that's it. I plan to work a little bit on the files here from the repository, GitHub repository.
And okay. May I clarify regarding the platform a bit? Hello, my name is Mikhail. Could you hear me?
Sure, sure.
Yeah, and when users design their platform, how they upload their design to the FPGA board? Because I understand the platform is web-based, like this website, right? And how it connects to the board.
Great point. What? Mike, is your name Mikhail?
Yeah, Mike.
Mike, we have done two things. We have created a device that loads the FPGA from the web browser. So, of course, you can download the bitstream and use OpenFPGA loader. We simply use OpenFPGA loader as Yuri, but you can use this USB device we created that talks to the web browser using the USB port and loads the FPGA directly from the web browser. Our point here is to go to a workshop, and any student using a Chromebook, for example, can connect the FPGA to this device and start playing without the need to install tools, configure, get permissions, whatever. Another possible approach is to use WebAssembly. We've been working a little bit with that, and it's already possible to use WebAssembly to run OpenFPGA loader on the web browser. We tried that, it worked, but it's too much slow. So it takes like 5 minutes to load a Blink example, but it's promising. The idea of directly running OpenFPGA loader on the web browser, there are some prototypes and some work that you can see somewhere on the internet. Finally, one last idea. There is a work from the guys of Tiny Tapeout, and they create a Verilog bootloader. It's very nice. It's a Verilog bootloader that creates a USB slave device on the FPGA. You just need a USB port directed D plus, D minus, the two pins of the FPGA port directly connected to the FPGA, and the FPGA, when you connect to the computer, acts as a serial port, because the Verilog creates a USB device that is a serial port. The browser recognizes that, and you can send the bit stream, and this Verilog bootloader will load the SPI flash memory, and you reset the system, and the FPGA loads the bit stream from the flash memory and runs. It's very nice. I can send you guys this link. Of course, if you overwrite the bootloader, you will need to write all over again. But it's a nice idea.
You have to get it in there in the first place.
Sorry?
You have to get it in there for the first time in the first place.
Yes, yes, you have to, yes. You need a writer for at least one time, a USB blaster or some kind of JTAG interface, okay?
Yeah. So thank you. I actually should say that we, like I was discussing with Edmund, who is working in Symbiotic EDA. By the way, do you know him? Just a second, I will tell you his name.
No.
You don't know him? He is actually very active, working on open source Govin and lattice-based projects. So let me show you his project. His name is Edmund Humanberger, and he works together with a person who wrote Yosys in a Symbiotic EDA. So he's commercializing open source tools for FPGA and ASIC. So he works with all those people with like tiny tape out and so on. And so we discussed with him a platform where he does all synthesis and place and route on the web. So one second, let me get discussion with him. So you see, they're putting everything called verified multi-platform gateways. So you just upload your design, and then they put everything on servers, and then you upload it to FPGA boards. And he wants to put our example as a demo project for his environment. So maybe you can also work with him and massage our example to be able to be supported by Yosys and so on. Like if you have some students for whom it's a good educational project, you can assign it to them. So you can talk about them if you are interested. So what?
Okay, thank you, Yuri. I'll talk to him.
Yeah, like I will forward you all this conversation, and maybe you can just look at his project and see how we can work with him. Because if you don't know him, he is well connected in like open source community for FPGA and ASIC design. So putting like anything joined on the in his project that gives us like leverage for like other projects. Yeah. Okay, so I will send it later on by mail. So let's actually get introduction from new people who came. So who are you and what are you doing? Hey, you're here. So, yeah. Okay, so tell about yourself. Yeah.
I work at Samsung as an analog IC design engineer.
Okay. Same building as on the North First Street.
Yeah.
Okay. So which floor are you working on?
Third, but I work with the guys.
So this is actually memory controller part, right?
No,
Ah.
I mean the display and sensor.
Display and sensor.
interface.
Yes, yes. I'm working on the fourth floor in a GPU. Yeah. Yes. So this is GPU part. Okay. And what are you doing?
I am Narayan. I work at Apple in system validation. So
Ah,
I
it's
work
a-
with the devices, all the new generation iPhones, iPads.
Okay, okay, yes, yes, good. Yes, I was actually doing some like contact for Apple back in like 2006 when we were doing like I was working in a company called Genali, and we were doing bus functional mother for verification of SoC for laptops system. Yeah, yeah, yeah. This is great. So, what are your goals here in terms of like Verilog and like Verilog exercises? So, what are you trying to achieve? So, let's start with you.
I want to learn system very well.
You want to, so, what is your current level in system Verilog?
Beginner.
Beginner, but is it like beginner, like total zero? Is it like you can put like A equal B plus C in sports? So
No,
what is
I
your?
do the very basic stuff.
So you can do basic stuff. So okay, okay. So and what about you?
Yeah, so I actually got my master's in specializing in basic design,
Okay.
but I moved away from it and into validation. So I kind of want to get back into it. So I would say like I understand fundamentals and I have some basics, but I haven't touched it in a while. Just want to like refresh it and like,
Okay, 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 good. So yeah, so what? Oh, by the way, you can introduce to like everybody else here because they know you. But
I'm digital designer. Just come here to support the group.
yeah, okay, okay, good. Okay, so the way how we work with the people like you is, so we have a set of system Verilog exercises which starts from the very like stage zero, and then we slowly proceed to the level of like interview questions. So basically, if you want to get a job in like our group in GPU or like in group in Apple, which is doing like CPU or GPU, you go to like interview and you are usually asked questions of a microarchitectural nature, like build some like a pipeline, connect with a five, or put some like arbiter and things like this. So, and there are multiple of known groups of such questions, and we actually have such questions as a part of our exercise. So you see, usually what happens like during like job interviews, you don't answer something what is in textbook. So like you're not like answering like write a five. You're like answering something kind of unusual five. Like write five with like undo or with like five where you can push two data in one clock cycle or one data in one clock cycle. Yeah, those like typical things. So or like a credit-based flow control topic which is not covered in textbook. So we are progressing in our system Verilog homework with such example, and I will show you how to run. Like and another way, because you cannot just do a simulation on like functional level, but you also need to care about timing. We have examples running on FPGA boards, and those examples are compatible with like open lane toolchain. So open lane toolchain is like open source ASIC design toolchain, and we can use it as a way to check timing, to check the maximum clock frequency. So we put like basic constraints, and we see how fast it runs. And now let me show you how to run simulation examples, and go to like FPGA boards. With FPGA boards also, let's get this gentleman because he may also need to listen this a second. somewhere. Okay. Oh, yeah. Like I wanted to show you because now like I will actually show how this all works. Yeah, books I will show you. Yeah. Okay, so now for like 3 of you, I need to, but like everybody, like else, like also can see it, but you can, but you saw it already. I just want to show how to run basic examples on FPGA board and in a simulation. Yeah, unfortunately, there are usually like 5 more people who are coming, and some of them have extra boards, but they couldn't come today. So I will have to show you other boards. So, but let's see what boards I have right now. Okay. What is?
Enjoying how to learn about that against the other things. I use packetology as my job. I am very interested. Very talking in this case. I used to be with jumping from microcontroller to FPGA is a huge job, and I am trying to do that. It started in January.
So let's get, for instance, Altera board. So we have support for Xilinx, Altera, Govin, Phoenix boards, and like in our activity, we are trying to like isolate students from a board, because for people like you who want to study microarchitecture, we don't want you to mess with setting up electric properties of the pins, and we want to go to like a level of these questions about like microarchitecture things. But for you, it's opposite. You are the person who isolates other users from dealing with the pins.
Isolate other users from the kernel.
Exactly. So now, and you see one interesting thing we have here. So here is like another set of boards with a Govin. So here we have a twisted pair interface, which is high-speed display interface, which is not working right now. We want to make it to work, and here we need to actually work with like application engineers from Govin to figure out how to set up those pins to work with HDMI interface. Oh yes, we are doing this already. Just we need to polish some support. So I will show you some like video things right now. So let's actually go through first example on FPGA and then example in simulation. Yeah, and so let's start because you ask about video. I will do video example because this is kind of cute. 1 second. Okay, so let me show how this all works. So let's get this board and let's get a display. 1 second. Where's my yeah. So I have this display, and I will use a VGA connector because that board has a VGA connector, not a DVI connector. Yeah, and yeah, so you can come here and just watch what I'm doing on the screen. Yeah, so here is a basic set of examples called basics graphics music. So this is like basic set of examples. And second. second. And I will show a fun way of learning system Verilog syntax by creating graphics. So such example works both under Windows and Linux. So in this particular case, we are using Linux. It's like every Sunday.
No, it doesn't publish in the meetup page that this happens. This happens every Sunday.
Yes. Like every Sunday. This is information for you.
It doesn't.
Okay. Usually it shows on the meetup page. Oh wait, you're talking about on a meetup with meetup website, or you're talking about meetup website? Huh? Yeah. Yes. It should be like a Hacker Dojo meetup, not on a meetup. A meetup of event. But anyway, yeah. Let me.
Every Sunday, 7 o'clock?
Yeah.
Okay.
Yeah, but like many people are doing this thing actually from home and communicate online. Okay, so now, so basic idea is that first of all, is my eyeglass. Yeah. Okay. So basic idea is we like isolate user from everything using scripts. So you can start like Visual Studio Code. You can simply use terminal. Like I frequently use Visual Studio Code because this is where many students do. So what you do is let's you like open the repository tree, and then you're going to labs, and in each lab, so let's get VGA lab because this is graphics we are going to show you. So let's close everything here. Too many screens. So here there is a top module, which we keep the same for all boards. So basically, we have a wrapper, we have a board specific wrapper, and we have top module inside this wrapper. So for each board, so we have like long list of boards. For each board, so this board is called D0CV. D0CV. So for each board, you have some board support files. And usually, beginning users don't look to those files, but those are files you need to create to support a new board. And in these files, there are some vendor-specific mapping of pins to logic names, and some timing specification, like you put this is like 50 megahertz clock. And then it has a board specific top in system Verilog. And this, so this board specific top, we specify how many keys, switches, and LEDs we have on the board, and then we put a mapping of all the like pins. We like instantiate module which generates slow 1 hertz clock, which we need for some examples. Then we instantiate our board independent top, and then we connect like a microphone and sound output to this board. But usually a beginner user who just started don't see this wrapper. I'm just showing you for the full picture. So now what beginner user does see is beginner user sees a set of lab examples. So this lab examples which start from like very basic with a couple of buttons and then go like multiplexer, decoders, and so on. So what is a VGA example? So in each such example directory, we have several scripts written in Bash. So those scripts, they can like simulate, synthesize for FPGA, synthesize for ASIC, and the script to choose another FPGA board. So you need to like open a terminal and there's too much stuff here. So you need to open terminal. I need to close this. Kill. Now, so start from. So you need to CD to 06 VGA. Oh wait, CD labs. So you need to CD 06 VGA. And then you need to then like you can see like this like number of screen, simulate, synthesize, configure, run GUI for FPGA synthesis. So and in this top file, this is what user actually modifies. And so here in this top file, it uses parameters about number of keys, then ports, then we instantiate a VGA module which generates synchronization signal. And this module also generates for us current position on the screen, so X and Y. And now in order to draw a picture, all you have to do, you need to create a combinational logic which determines color for a pixel. So this module generates for you X and Y, and you tell color for the pixel. So in order to draw a rectangle, what you do is that you check that if X is more than 100 and Y is more than 100 and X is less than 150 and Y is less than 140, then you put green as all ones and you put red depending on X. I have actually simplified example, but you can put here just red some number, just to put this construct to make redness depend on X. I'm just getting bits less. Huh?
It's going to be a gradient.
Yeah, a gradient. Okay, so now in the same way you can draw a circle by specifying that if X and Y is within circle, then you do like everything red. Then you can draw parabola, and now if you add counter to it, those things will start to move, you know, and then you can put more code and create a game out of it. But essentially, yeah, so like essentially what you do here is that first you choose a board. So you just put like 06, choose another FPGA board, and then like it asks you what board you want to choose. So this board is called D0CV. So this is board number 10. Didn't run it for a while, so this may not work, but let's see. Okay, so you synthesize. So this like automatically found Quartus installed. Or for Xilinx, it will find Xilinx Vivado or Govin ID. So it looks for usual location, usual default installation location, or it allows you to specify it with environment variables. But in this case, it just found a quartus in default location and it runs synthesis. So this will run for some time and then it will upload design to the board. So let's wait a little bit. Yeah, Xilinx is slow synthesis, Altera is less slow, and Govin is very fast. So we'll show you Govin as well. So actually, it's a good way, it's a good and fun way for beginner to learn syntax to draw such pictures. Because I mean, you can of course start from like LED things. All right, so you see, so it's like a draw here things. So now let's make the thing moving. So we have a dynamic pattern. So here we have a module which generates strobe signal 10 times a second. And so we like add count. So this is essentially counter. We add counter. And this pattern can move, moving pattern. So let's like uncomment this thing. So let's like uncomment this. Let's uncomment this one. Let's synthesize this again. So yeah, so those are synthesis examples. So once you go through such synthesis examples, and if you modify them, this is one way of learning syntax and also looking to timing. Now, like I will also run GUI and show you how GUI shows how you synthesize the thing. Oh, this one. Okay. Okay. Okay, so you see, so now you have a moving pattern. So you simply connected the counter to this calculation, and you can see some pattern. So you see now from such like a very basic setup, you can actually even get like a bunch of students and they can train their fantasy what they can do with it. So now, what other scripts do? So we have a script. We have a script run GUI. So you do 05 run GUI. And this we run a Quartus GUI. And you can do everything in Quartus GUI, but like as we all professional know that in the companies we just run a bunch of scripts instead of constantly like working in GUI. But so we can do same thing in here. So this like loads automatically. This loads automatically project. So now, okay, let's see, was it runs netlist viewer or was it need to run synthesis for it? Ah, no, you have to rerun synthesis, just a second. Unfortunately, we have to rerun synthesis in GUI in order to see schematics. Yeah, with some GUI, like with Xilinx, we don't need to do it, but this GUI is a little bit finicky. So it runs analysis and synthesis in GUI. So like it does everything what our script does, just in GUI. So now it will run filter, and you can see how your RTL synthesized. Yeah, so now you can go to this like netlist viewers, RTL viewer, and first you can see how synthesis elaborated, and so you can reach the top. Oh, wait, what is this? This
Is the diagram automatically generated from the code?
yes, during synthesis. This is it getting the right? It's getting the yeah. So this is actually our logic. Yeah, and you can see here that it gets our Verilog code, and it doesn't map it to FPGA cells, but instead it map it to like abstract logic, so to multiplexers, D flip-flops, gates, and so on. So now you can see logic inside the strobe generator. So next step, so this is the first step of synthesis, elaboration. So it gets HDL, creates this thing. Now, second step, it does mapping. Wait, I have to close this. Oh, it doesn't let me to close. Ah. Okay, so second step, you can do a technology map viewer. So technology map viewer is a step when it actually mapped our logic into cells, into specific FPGA cells. Yes, this is a top. Yeah, so you see, if you go here, you don't see like a multiplexer. You see a lookup tables in FPGA. So it moved to logic of specific FPGA. So this is a device-specific thing. So for different families of FPGA, it will be different cells. And now, why it doesn't let me to close it? Let's technology map here, so let's close it. Okay, so now if you go to chip planner, you can see how those cells are actually spread over FPGA, so you can actually go to specific cell. But usually logic designers never look to here. So basically, I'm just showing it to you because if you do some logic and if you want to see how your Verilog code synthesizes to a specific netlist, you can, in principle, go to such viewers and see it. Yeah, but usually we don't do it. It's just an option.
The elaboration view, the cell view, are they shown only in Argus or other softwares like Xilinx?
Yeah, you can have same thing. Yeah, you can have this in Xilinx. You can have it in Govin. Yeah, so like I just got this board because this was first board. Like I got today. We can show same thing with the Govin. So now, now we can also synthesize the same example for ASIC synthesis. Just a second, just something new. Yes. Okay, good. Okay, so now we can close this GUI and we can go to ASIC synthesis. So for ASIC synthesis, actually have example with a CPU. So we have example with a liter CPU with a school RISC CPU. So rest of examples, not all of them are yet compatible with ASIC synthesis. So and you see for like our Samsung chip like as well like a sample. So we're using like Synopsys and Cadence tool chains, but they all cost like millions of dollars of fees for the company. But for like experimentation and research, it's enough to use open source, open lane tools. Those like open lane tools, 5 years ago, they were very poor quality, but now they're like pretty good quality. And I will not run.
You can produce a real.
Yeah, you can produce a real chip. Yeah.
That is feasible to do in low quantities.
Yes, this is feasible. So what actually happened is, for some years there was a shuttle service provided in US by a company called Moses, and in Europe by Europractice, they like allow researchers to put their research projects on some shared die and do it for low price. So like instead of spending like tens of $millions on 3 nanometer chip, you spend just like several $1,000s for research chip. And now Google several years ago went into partnership with a fab called Skywater, where they like allow students and researchers to make chip for free if Google likes their design. So there is a website which like designs, and if Google doesn't like your design, you can still do it for like less than $10,000. And now there is a next step.
Having the design to get the chips.
Yeah, you can because it's a shutter service. This is not like urgent. This is put as a, like on like available capacities after commercial things. It may take like half a year, but you can still get your final chip. Now there is a next step. So first of all, I will show you. Oh, let me share my screen.
How many chips they gave?
I am not sure. It's like several chips or so.
Yuri, I know that.
I'm not sure. Yeah.
Yuri,
How many chips?
I have
Yeah,
already done some.
Rafael knows because he was using it.
Yeah,
So
I
can you
already
tell us
used it.
more about this? Let's put sounds there.
Yeah, Yuri, I already used that service. It's $500K, and you get 100 units encapsulated.
Just a second.
Encapsulated.
Like I want to put you on speaker so like everybody can hear you.
Yeah, can you repeat that? We just put the speaker.
Yeah.
Okay. Just to add something to the discussion, you can talk to a company that's based on the Bay Area called eFabulous, and for $10K, you get 100 units fabricated and encapsulated. So it's quite affordable for the semiconductor industry, using OpenLane, as Yuri said. And they are pretty reliable right now. They're getting good design fabricated.
We're having a lot of noise in your line.
I just need to put my microphone on mute. 1 second. Let's put my microphone because otherwise we hear noise. 1 second.
Yep. Okay,
Yeah,
Rafa.
can you hear me better now?
Perfectly now, much better.
Great. I was just adding a little bit to what Yuri said, that there is a company in the Bay Area called eFabulous that works with Skywater, as Yuri also said, and you can use a service called Chip Ignite. You pay $10,000 and you get 100 samples fabricated and encapsulated and a dev board with that chip. And people are doing some great stuff right now, digital and analog. And of course, as you already said, you can use OpenLane. It's pretty advanced right now. It's getting each time better. And I've done a RISC-V design and fabricated using our chip inventor here that I mentioned. And we think it's a great opportunity to get 100 chips for $10,000. It's affordable for the semiconductor industry.
That sounds fantastic.
Yeah, that's it. That's what I wanted to add. Thank you, guys.
Oh yeah, thank you very much, Rafa. eFabless. eFabless.
Yeah. Okay. Can you hear me?
Yes.
Yeah. Yes, I got disconnected. Okay. Okay. Now, one more important thing. You can also use an option called tiny tape out, and which is the next level of cheapness. So instead of one person spending $10,000, you can have like 50 people who get a tiny fraction of the common chip, and each of them pay like $200. So
Oh, but it's all on the same die.
yeah, this all on the same die, but this has like a multiplexer, so you can just choose which part to run. So they provide the interface that you run, and then they give like everybody. So just bunch of people pull common pool on such chips. So this is tiny. So this is tiny tape out. And yeah, maybe we can put one of our examples to this thing. Yeah, see, so no more $10,000. So you can do everything starting from $50. So this all like depends on size of your design, but you really need to put like a small design. So now if you go back to our if you go back with here, yeah. So if you go to school RISC-V, so 30, yeah. So here I don't want to run the whole synthesis right now because it will take too long, but I will just show you on screenshots and like reports we are getting. Oh, like wait a second. I think I synthesized this already. So let me just run this is good. So you can like visualize the result of synthesis in K layout, for instance. Let's see. Yeah, so we have here, you see, so the synthesized chip in GDS2 format. So exit, or you can synthesize it with a different tool. Yeah. So with a 09. Yeah, you can visualize it this way. Now I will show you what kind of report ASIC synthesis produces. So I ran it before. Wait a second, did it create reports here? Oh, unfortunately no, because I was running synthesis, it removed reports. I need to run it again. Anyway, you can see some screenshots about reports. or I have those reports, or we can let it run synthesis right now while we are talking.
The images are here as well.
Yeah, the image is there. Okay, so we can actually run synthesis. So synthesize for ASIC 07. You can see what kind of report it's running. So it starts synthesis and it does the synthesis, place and route, and produces a critical path report. So this is a way to teach students about timing in ASICs, because like of course this is not kind of equivalent of Synopsys design compiler, C compiler, like Cadence, Genus, Innovus, but they can get concept of like critical path. They can get concept that if they do too large like multiplexers, they will not fit into a timing budget, and they need to learn how to restructure design to fit into this budget. Yeah, so this is like basically a basic flow with our example.
This is like STA.
Huh?
Is this like STA?
They have a static timing analysis. So now we are running everything. So synthesis, elaboration, STA on several places. So we run STA after basic synthesis, after place and route, and then like after everything. So this has like 40 steps, and there are like STA reports at least at 3 points. Yeah. So you can so basically for these examples, what we are doing here as a group, the intention of these examples is to be used in a university programs and in a seminar. So sometimes I'm going to different countries. Like on February, I was invited to like Azerbaijan and was running seminars there. Now I'm talking about the same seminar in Uzbekistan, in a university named after like scientists who invented algebra and algorithms. So so they want to make this seminar maybe on like October. This is like a tentative, but we can go there now. One goal is that we want to remove vendor lock for the professors, because what happened now is that Xilinx, so like Altera representative, sells something to school, and then professor create his like curriculum materials, and they're linked to this specific board, and he cannot change it for decades. So, but now with this example, you can switch board. You can use this board and switch to different vendor right away. So this is like one thing. Second thing, by like interviewing students, I found that many have problems with the microarchitectural questions, like about like credit-based flow control, pipelining, and so on. So we have examples in this area. Yeah, specifically Kieran, who is on call, yeah, he can maybe tell like a little bit. He put a post into our website, and I am trying to catch Cliff Cummings, who is famous trainer in Verilog, to figure out whether we can create a joint paper in it. Because we are trying to work with FPGA vendors, so on like next this coming week, I'm going to meet with the Govin USA people, including president, and talk about those board support. So they call like kind of activities, and because those activities, they're all open source, and they're all based on non-proprietary things. This is a way for people who want to learn Verilog to learn the things. Because I'm reviewing your code, I can guarantee that in terms of some tricky things in Verilog, like in like system Verilog, you can have some tricky things in like generate parameterization, like interfaces and something, so I can review your code. Yeah, this is kind of what we are doing. Yeah. So yeah, and like also we created this little website, verilogmeetup.com, and now the reason I created this website is I want to get a booth on a makers fair, which is like for hobbyists, but this can like targets general public. And last year I saw in such a booth senior director of NVIDIA, who also has a side side activity to go to like Arduino, a kind of show and create. Like actually, I put here in post photo with him. So if you go to articles, wait, let's click on. Wait, it doesn't let me. Why doesn't it let me to click on this? A second. Yeah, here. So just sometimes under Zoom there is some problem. Let me close this thing. Move this. Everything is not clickable. Just a second, I will stop sharing screen. Okay. Yeah. So now it works. Yeah, it's a Zoom interaction with the application. Yeah. So I actually put. Yeah. So this is actually a senior director of NVIDIA, and he put some. This like Geiger-Müller counter which connected to FPGA board. So actually I got the idea to have such booth in a maker's fair, and just to go there and show all those demos with graphics, with a microphone and so on. Yeah, but in order to like support this activity, we need to support many boards. And we need to create a new example. So let me show you example with like a micro architecture. Okay, first, you see this is still running a detailed routing. It's a slow thing. With the micro architecture examples, let me get another terminal. We just midnight commander in this terminal, so let me run projects labs. So here is a valid ready, etc. preview. So let me show you demo of a FIFO on the same FPGA board. Synthesize. Yeah, so this is kind of active. Yeah. So now let me show you system Verilog homework, because this is something what they want, like everybody who is training in Verilog, like what they want everybody to do. So so system Verilog homework is a Git repository. Okay. Let me stop share this and let me share desktop. Yeah. Sometimes it doesn't share it, right? Okay, so system Verilog homework is a repository. Okay, so first of all, let me show you how this FIFO works. So you see, it just shows here like empty FIFO, and then you press a button and you push things into this FIFO. Then you press another button and you remove things. So this is with some demonstrations. Then we show how FIFO full and FIFO empty. And then we put some like pipeline designs here. And we have like examples with the 7-segment indicator. And also by using UART, we can put these examples to computer. So and in such examples, so you like implement a FIFO module, and then you instantiate this FIFO and you connect it to like 7-segment indicator. And we also have a test bench. So we simulated. So we have test bench and we teach students basics of testing their design. Because what actually I found from many recent college graduates is that when they give them some questions, like interview question, like you have like two like one narrow like excite channel and convert it to wide excite channel. And many of them cannot verify such design against corner cases. Because in the school they are taught only direct case approach, where you just put some signals and look and wait for what happened, and they don't think about all the corner case scenarios. So to do all, so basically you need to learn them that they need to verify it against some model, against some like monitoring model to verify response. So here I created example of FIFO monitor, which is a simulation only code where you're using system Verilog queues. So it's a special like syntax with a dollar for a queue, and then you use like assertions to check that you don't pop from empty FIFO, and you check. So you check on signals when you push. You also add data to queue. When you pop, you remove data, and then you're doing some logging. And then we do a test benches, and these test benches we do direct tests like we full and empty FIFO, and then we are doing randomized tests. So we are doing like randomization constraints. So they many like students have to be taught properly with the verification. Yeah. So now let's go to the homework exercises. So you can something which you can start right away. So those homework exercises require only Icarus Verilog. It's thing which you can install in Linux by sudo apt-get install iVerilog, or for Windows you can download from website and run it right away. And then you run script. So now let's go through the first exercise, and I want you to go through all of those exercises. Yes, you can just go to GitHub, and you can go. So let me. The instruction was in Russian because I was using it in Russia. Like I was doing many seminars in Russia, Ukraine, Kazakhstan. They all like in Russian, but this is only like top level instruction. You actually the tasks are specified there in English. Yeah. So So this is actually used in right now in 20 different Russian universities. So like I'm like half Russian, half Ukrainian. So like I lived both in Kiev and in Moscow, and they came to the US like 33 years ago. So now when I was working in a MIPS, in a processor company, so MIPS decided in 2009 to like explore a Russian market, and because there was only one engineer around, I went with the VP sales to Russia, and we like eventually made deals to license MIPS course to several like Russian companies, and creating a chip called Baikal T, which is the only one Russian superscalar CPU produced in like some more than test amount, which is but when I was doing this, I went actually to their universities, and they found that their curriculum is not good because it's missing many parts. So I proposed them to translate Harris and Harris textbook, and then because I was also a co-author of MIPS FPGA package, which was created here in California by professor of Harvey Mudd School in Southern California. So like I was in MIPS specifying document for them how to create it, and then they created it, and then we use it here in US, in like Southern California, in Portland State, and in China, in Europe, because MIPS was part of a British company, Imagination, so we used it in Europe a lot, and in Russia as well. And when I went to Russia with MIPS FPGA to like all their schools, so like I know like every single important school there who is doing this, I found that they don't have good basic exercise, and then started to create basic exercises, and then I found that such basic exercises I actually there is interest like in other countries, like in like Italy, in Israel, like in Vietnam, like some other people. So we started to put together this like package, and yeah, this is in my repository. Yeah, now this like Russian-Ukrainian war started, so this all became complicated. But some of contributors here in some like previous examples were from Russia and some from Ukraine, and created some joint even textbooks. So now it's all complicated because even those who are like they're kind of the same professors, but for example, dean of Ukrainian university cannot publicly and even not publicly work with the Russian schools because he like ostracized by their like administration. Plus, in Ukraine, there are universities on different side of front line, and some of them, like Donetsk University, half of university went to part controlled by Kiev, and half stayed in part which was annexed by Russia. And both of them have FPGA labs. And both of them have like professors, but they cannot talk to each other. And I cannot talk with them as well, especially with Donbass part, because I'm restricted by US sanctions, so did with anybody on like Donbass territory, you know. So so like things went weird there, you know. But like anyway, let's take system homework. Yeah, so you can just get it here. Yeah, here is instruction. Here is instruction in in Russian, but you can ignore it. It just simply doesn't say anything important. Let me just tell you what you need to do to run version of Icarus Verilog 12 in case it's not automatic, in reference to the textbook. But basically what you need to do is that in Linux you need to do sudo apt-get install Verilog GTK wave. However, you need to use relatively recent version of Linux to install Icarus 12, because Icarus 11 has some bugs which are important. And if you want to install Windows version, there is Icarus Verilog for Windows. Here. So you simply download here 12 and they can store it in one mouse bar. And this works even under Apple Macintosh. So our scripts supported under Apple Macintosh with a brew. So you set first brew, and then you run it on brew. So if you look to now how to run it. So you simply put Icarus, and all you have to do is there is a script called run all using iVerilog under Linux or macOS brew. You see? So you just do run all. This is all you have to, this is all you need to know. That's it. So, and then now it says that Mark's question pass. So wait a second, did I solve this question? Yes, I did. So basically, for each exercise, you have some change to make it pass. And once it all pass, you can send me email and I can review your code. So this is like question number one. So you put module in Verilog. So this is like input 4-bit D0, D1 selection and output. And in order to implement multiplexer, you do y equal select D1, D2. Okay. Now write the same thing for choosing 1 out of 4. So okay. So familiar with the basic syntax of Verilog? Hardly. Okay. Yeah, this is good. So now let me give you immediately book recommendation, and I can loan this book to you right away if you don't have it. Basically, if you want to start from absolutely beginning, what you go is, so you go to Verilog Meetup, and you go here to post called self-education and educating others. And here you're going to list of how to self-education. So do all homework here, run and review examples here. And like if you don't know, rest is like secondary. You need to start from 1 and 2. And now books. So first of all, there is a good book called Digital Design and Computer Architecture. The good thing about this book is that it has like effectively 5 books in one book. So it teaches basics of digital design, teaches basics of Verilog, basics of VHDL, and how to build a very simple CPU. Okay, but for you, because you are already professionals, many things you can skip all the up to chapter 4, or instead of this book, so let me show you this book first, or you can get book by Donald Thomas. And for microarchitecture things, there is also this book, plus you can use Verilog standard, and you can get articles like Verilog Gotcha and articles of ClickRN. So I left everything here. So if you just follow this, you will get a solid understanding. So now digital design and computer architecture is a general purpose introductory college textbook, which is a combination of basic digital design courses with Patterson-Hennessy type. Oh, did you study Patterson-Hennessy textbook in school? So, I'm talking about a book called Patterson-Hennessy Computer Organization and Design. Yeah, this is one of like standard US textbook, but Harris and Harris is a kind of this book plus something else. So that's why I have slight preference. But we would have seen the fifth edition, the cover of the fifth edition is much more familiar. Okay, yeah. But anyway, this is a book which I recommend to use as so. Just like in C, there is like a Kernighan-Ritchie book, and this guy Donald Thomas, he wrote back in 1991. He wrote a sort of Kernighan-Ritchie of Verilog, which is he wrote book like everybody was using in like early 90s to study Verilog, including myself. And now he wrote. So he put like 6 editions of his book, and now he wrote another book, which is different one. So this book is not a new edition of his old book. And this book, Logic, Design, and Verification using System Verilog. And for people who are like already familiar with like C and I think this is kind of one of better books to start reading, particularly because he explains how a simulator works, which is useful. Yeah, so I recommend. Oh, I didn't bring this book. Yeah, so I recommended to order this book. So it's like solid choice. I will bring you. I will bring this book next time here. Yeah, actually, I actually had this book for review because I did recommendation for the Russian translation, but I cannot share it. Yeah. Oh wait. Like I can share you. I can share you some. Just I want to show what is the first 3 pages. Yeah. So like I was talking with the author, and yeah, this book. Oh, wait. Yeah, okay, let's see if I can find some edition of this book to show you what it has on pages. Okay, press. Oh no, this is something else. Second. Press. Oh, it's gmkpress.com. Yeah, good. They have PDF for some first pages because they actually made contact with the author through me. They will just show you what is on the first pages, so you will get the idea about what is there. Okay. Okay, let's see if they have some PDF preview. Sure. Yeah, they do. Okay, so yeah. So I will just show. Oh no, they have only at the end. Yes. Yeah, so you see, they actually start from the beginning. So they put some modules and ports and some like basic syntax, and then they like show how this is interpreted, how you get schematics for it. So they like explain it this way. Then they show how to do this in simulation, and so on. Yeah, so this is a good book. So I will bring a paper version next time.
That's a fairly small introductory, simple. It's a small introductory book. It's in the US, it's in paperback. It's about that big, about that thick, right?
This is actually not small. If you want a really small book, this book is like this size. It's not really small.
That's something else.
Yeah, but I think I know what you're talking about. I think you know. I think you were talking about. Let me show you book. You were probably talking about. There is a book. You're probably talking about this one. Yeah, this is actually a good book. It's a really brief introduction. The only problem is it has syntax of Verilog 2001 instead of System Verilog. But it doesn't matter. You just need to keep in mind that to go to System Verilog, you need to instead of reg use logic. Preferably, also local examples here will work with. You can use this one if it works for you better. So this is like nice clean book, just kind of uses all the version of the language and maybe just a little bit too basic because you will go to next step very fast. But the good thing about this book explains PLL blocks, which like other beginners book don't explain. And we do need PLL, for example, to connect some of boards to the external monitor. You need to do PLL because you need to like increase the frequency to 125 megahertz from 50 megahertz. Now let's go back to these exercises. So like basically what you do is that when you run code for this exercise, and when you each exercise has a self-checking test bench. So this has a test bench which just puts stimulus so that it checks that your thing basically works. But even with this basically works, many people they have they do like other mistakes. So that's why it needs to be reviewed by a human person. Now, like it shows you that now like this goes through various syntax. So you can do this max with a ternary operand, but you can also use combination of always block and if statement. So this is second way of doing this. Or you can use case statement. Or you can use index out of two-dimensional array, which also ensures max. Or you can use it using gates. So you see there are like 5 different ways of do the same thing. And by doing this, you learn syntax. Now how to build a divide the max from 3, how to build a selection of 4 out of 3 maxes for 2. So those are all like basic textbook questions. And finally, we are going to actually interview question. So this is already question used to screen by some companies before. Now they don't do it because it question became too well known. But yeah, but this was like nice like tricky questions that you can implement Max using gates, but can you do opposite? You have Max as a basic black box, and you need to implement gate using Max, using only instantiation and constants. Yeah, so yeah, you can like train yourself in this thing. Now the same thing about torque. So this is the first level exercises, and you just do it. Then you run the script to like under. So it says that everything failed, and once everything passed, you send me email with a solution. Now, same thing about Windows. There is a script to run it on the Windows. Now, like almost all go well through 0-1 combinational logic, but people start to get bored and quit when they go to sequential logic. So sequential logic starts like easy, so you can detect positive edge. And here is a beginner mistakes that many people who learn Verilog, especially if they did programming in C before, they put that they detect edge by putting like always at edge data signal. But this is you can write it in Verilog, but this is prohibited by design methodology. So according to design methodology, everything should be synchronized by the clock. And this is one of those things you need to learn about Verilog. Because in Verilog, it's not only language, but it's also a way how you have to do things to make design reliably work on the board. Because if you, like I saw many beginners who didn't read books, didn't do exercise, they just started messing with the code. And they were putting here like always at data signal, and some tools even synthesize it, make it warnings, and then they ignore warnings, and then it does something strange on the board because of purely like analog things, because it puts D flip-flop into metastable state and doesn't produce correct output. Yeah. Now, then you generate Fibonacci numbers. Then you this is interview question I'm using frequently, and the bizarre thing is that there are this is like basic question, screen question. So if person doesn't do this in 10 minutes, it makes no sense to ask you complicated questions. So, but so first, like I'm sorry, I know that you got master degree and stuff, and this is too basic for you. But we just ask people as a screening, then I will ask you something more interesting. So now the question is that you are getting 2 bits every clock cycle, like A and B, and you need to produce some of those bits. So this is serial reader. You just get 2 bits. You need to keep carry to generate carry and produce sync with the carry. And now, but in this exercise, I actually show solution how you do this with the plus operation and carry, and then to ask to do this using logic operations only. This is actually a simple variant of this. But the problem starts when, this is my actual interview question, the problem starts when I ask people to add valid and last signal so that you register only inputs when valid signal is high. So in which case you send bits not every clock cycle, but you send bits together with a valid signal that is like valid. So people
What is the last?
last just means this is the end of one addition, then like another pair of numbers start. So you should like reset carry and start from the beginning. So this is kind of nice exercise. Yeah, this is serial comparator, another screening interview question. Useful. And so on. Then there are some like finite state machine, and finally by 4, we are actually going to something interesting. We are going to something which I described in this article, post which I wrote like last week, and even put into here, so-called focus on microarchitecture. So basically what I found is that if you get E student, and this is applicable like typical bachelor degree student, even with expensive top universities. And when you ask them that here is a pipeline block with a latency n, so you put just like x from one side, and after n clock cycles, you get square root of x from another side. So now when I ask them to like implement a circuit which adds 3 square roots, they like answer it just fine. But if you ask them to do a circle which implements formula with dependencies, they start to I mean, not like all of them, like good. So like top students do this fine, but like half students don't know how to do this, and then start to come up with all kind of like strange ideas. So like I listed here strange ideas. First of all, they just connect blocks, ignoring the fact that by the time you evaluate square root of C, B is gone. You know, so they need to delay arguments, but they were learning in school, like in like second year of school, in like shift registers and FIFOs to like delay argument to the appropriate pipeline stage. But for some reason, this knowledge is just hanging in their brain in the vacuum. So they just simply do not connect it with like other things. And then, so basically what they need to do, so they learn FIFO, but they don't understand that they need to like attach FIFO to just hold somewhere other data before further processing. So once I start typing, also you can put shift register. This is also correct answer. Circular buffer is correct answer. And actually, like if they get puzzled for like more than 10 minutes, I start to ask them like 15 minutes. Like I start to ask them, have you learned in school FIFOs? Yes. Can you write code for FIFO? Like, have you learned shift register? Some don't remember it because this was too basic. And says, wait a second, I can use FIFO to hold those arguments. So, which is a good case. But there are cases when they some put that they had student projects in like out of order CPU using Tomasulo algorithm. And they said, oh, can they use Tomasulo algorithm here? It's like using like I don't know, like two-story bus instead of like bicycle, you know. So this is like too much overkill for such a simple thing. Yeah, and so basically we had this set of these exercises, and Kieran, who is a person on the let's see, is Kieran? Yeah, Kieran is still on the call. So he is working with me to create like extension of such exercises. So he put here like case study on effective pipeline design, putting about back pressure. So there is a book on Amazon called this one, William James Daly and Harting, and this is used as a textbook in Stanford. So like I bought it from Stanford bookstore, and this also is used in MIT. And this book actually has some of this stuff, but not all of it. So it doesn't have the credit-based flow control, which is used on all like large electronic companies, but they don't use beginner students on job interviews because students don't know it. But this is a must question for like senior engineer. So, but he like doesn't know this as well. But in this book you have like double buffering and flow control, and so Kieran put some example of this in like examples we work in this project. So what is back pressure and global stall, have performance buffer and skid buffer, and two depth FIFO and design example. Yeah, and this is actually like half performance buffer, and the skid buffer, which is double buffer, is described in this book, but it doesn't describe many things. But this is where we are going in a set of exercises 0-4. And now set of exercises 0-5, and some of them with FIFOs and some with a simple CPU. And this is actually kind of interview level homework. So if you want to so you see, all those students, they have in their like resumes, oh, we did 5-stage MIPS pipeline, the Masul algorithm, AXI interconnect, something is cache. Like then I ask, okay, so you have a toy CPU with 300 lines of code. So in this toy CPU, you have like a LU for 5 commands. You have like control unit for 10 instructions. You have like decode, which decode fields instruction. You have register file, which just stores register and has like access to register file. And you have CPU instantiating policy. So this is the simplest CPU you can have. Okay. And now my question is, you put so much student projects about making sophisticated out of order CPU. And now can you modify this CPU to if you multiply with a multiplication instruction? Say, yeah, sure, easy. Just put one instruction, it works. Yeah, but now your multiplication should take not 1 clock cycle, but 2 clock cycles. So not like a combination, but with a latency of 2 clock cycles. And at this stage, only one person did this right. And he was hired by Samsung this year. Because he properly put all the forwarding in a like a rudimentary pipeline combining both like pluses and multiplication and so on. So this question sounds easy, but students even after like supposedly complicated projects don't do this right. And actually, I can show like one like anecdote that one like person to solve it. Like I think this person was probably using Chat GPT or something, because I cannot imagine how a person can come up with such idea. So this is like funny idea. No person would I mean, no professional would even think that you could do something like this. So what she did is that she put like multiplication module clock multiply 0.5.
Like slower clock.
I mean, clock is a one bit signal. You cannot multiply it by floating point. Huh?
Is it synthesized to something? No.
Of course not. But I mean, if you propagate it as an integer, it will be zero. So this will just turn or block. But this is not the point. The point is that by the way, 4.0 student. Yeah. So like all A student. So like expensive university. So, but you see, the theory probably don't have enough like practical exercise, or like maybe didn't want to.
But this work in simulation or like what? I don't
No,
get it. Like
no,
what should happen if you do
this will not work in simulation.
Yeah, so like
RC delay on the clock.
Yeah, kind of. Such happen. Yeah. So yeah, you see, so like basically we need to
Do we use EDA playground for all the simulations?
huh?
Do we use EDA playground? What is
yeah, you can use EDA playground, but I'm using Icarus Verilog. Yeah, so Icarus Verilog. This is just so Icarus Verilog, iVerilog. Yeah, so you can just install it in. So you just do it like sudo apt get install iVerilog, or you can download it from website Icarus for Windows. But you can do this in EDA Playground too, because many companies do use EDA Playground for interviewing process. So they're all compatible. All those examples are compatible with EDA Playground.
So the test benches are there for.
Yeah, so test benches here, and for CPU, we also use a simulator called RARS, which is a free simulator of RISC-V. So you get okay, where is the assembly program? This like program. It's like simulator with like 3 buttons. So you can press F3 to compile, and you can put F7 to step. So you put like F7, and then you see how your instruction goes and change registers. So for CPU examples, we're using this, and you can actually export using this. You can actually use this simulator as an assembler. So you just you just use it with the following command line. with this command line, it will produce a hex file out of assembly file.
But is it like somehow connected with your architecture, or it's some?
This program is loaded as a program for our RTL code. So we're using it to test it.
But like this RARS, it simulates.
It's instruction set simulator. It doesn't simulate Verilog. It's just to debug assembly programs.
Okay, so like whatever you wrote in Verilog should be compatible with what's happening in this RARS, right? Like
Yes,
things should.
Yes. So you can use this RARS for verification. Yes. So we essentially use RARS for verification. Yeah. So those are like once you go through those examples, you will get to the level where you above average candidate like in interview. So and actually doing this is not that difficult. You just need to in parallel read the textbook and that's it.
This is primarily this textbook.
You can. I mean, like, this like textbook goes deeper than others, so you can start from Donald Thomas or even from Harris and Harris. So Harris and Harris textbook is probably easiest one. Yeah, but Harris and Harris is not very good in a Verilog in like explaining like everything in Verilog. Yeah, one Harris. Where's my okay, so go yeah. So you can really look to different books to see what works for you, because for some people what works is reading like chapter 4 of digital design and computer architecture. For some other people using Donald Thomas for basic syntax. Some people can get like very first thing using that book. Wait. Use that way, but you can first try chapter 4 of this book and see whether it works for you. Yeah, I can bring next Sunday all 3 books, so you can just see what book works better for. And then like I recommend to go through those exercises by combining those exercises with FPGA boards, and that thing you will get up to solid level like after some time. Like of course it's not. Oh, by the way, another kind of interesting thing which many students lack is lack understanding of like generate, because many professors kind of not interested in explaining it. So there is a construct called generate, which allow to generate flexible parameterized designs, and especially like with parameters. So you just like a parameterized design by width, then you use generate to instantiate blocks conditionally and stuff. So this is some syntax which is kind of easy, but for some reason many schools don't teach it. Also, it's needed in industry, and many companies, instead of generate, especially those companies which use legacy code for like 20-something year code, they were using embedded Perl or like Python generators for the same reason. But I personally think that you need to use generate unless you absolutely need to use like embedded Perl or Python generators. Yeah, so this is kind of some basic kind of teaching. So what is your, so like I said, next result, I recommend to read that instruction, start to go through exercises and send me exercises, and then you can see from list of projects what like project you can take. And so here, like I have some list of projects, and some of them are already done, and some of them are not. Yeah. So and like I have like 50 different boards, and some of them are supported and some are not. So we are just looking to various problems solving with those boards. Okay, so now what are your thoughts? So how do you how do you see it? Is it like something you like expected, or you like any like questions?
I don't have anything, but I'm so I some of the exercises. So I did some of these exercises before.
Yeah.
But for the books, like, what would you recommend for a book? Let's say if I don't know anything about any microarchitecture at all, and I would like stuff like you were saying, like where you would want to do like with latency and all that stuff. So that, what kind of book?
Yeah, the thing what really is bizarre is that this thing is not explained in like any book in a good way. This is all asked by like Apple, Nvidia, Samsung, Juniper, during like job interviews, but this is not explained in textbooks. So there is a recent book published by professor in Cambridge. So part of it is in like just a little bit of it is in this Stanford textbook is in this one. So this one I definitely recommend to read chapters because this is a good book. This, but this only goes like 20 or 30% of where like it should go. For instance, but there is like another book, and this is book you can download from ARM site, and it's this one, Modern System on Chip Design. So this is a new thing, and you can simply download it here. But the problem with this book is that it doesn't have examples. So the code example. So it explains everything in words. So you see, if we download it, let's see if I download it. Yeah, you can just download free textbook. Maybe I haven't really downloaded something somewhere. Let's see. PDF. Yeah. No, this is ARM fundamentals PDF. Nano spec. Yeah, this one is a different book. Okay, SOC. What is this? This is something else. Just I want to show you, for example, what credit-based flow control. This is kind of a predecessor to this book. This is kind of easier book. Yeah, but this also covers some topics. Just a second, let me see. So let me see, like if I have downloaded it, because I can, because I just don't want to force time to fill this form. So documents, pictures, templates, better going repos, literature. Oh no, this is Harris notes project scratch them. If you get this book, it does have a picture. Consumer electronics semiconductor. We just do this, then get so this book has actually one good project is to get text from this book and put it into code and put it on the board, because really you need like students to play with the board to actually understand what they're doing. SOC. I received this link before. Well, like basically you're getting link and you download it, and it does have things about explaining like interconnect, like bus protocols ready. Oh, wait, I did one thing. I put body. I should do it. I'm talking about book. Just a second. Yes, this one ARM. This wait. I need to. Yeah, I can download. Yeah, okay. Yeah, this. You just need to press button. You don't need to check it. You just enter your information. You press. Okay, so this is the book. So let's actually download it here. To downloads. So you see here you can search for credit-based flow control. Yeah. Put here. It is recording. Okay, so doesn't matter. Anyway, so okay. Okay, so if you look to this book, if you go here and look credit-based flow control, so this does explain credit-based flow control. So page, yeah.
Is that the only thing you recommend reading?
I recommend reading. This is one of good books, but you see, it doesn't have any code. So basically, somebody has to put it to code. So here, okay, standard synchron. So like it explains things in. Yeah, so like it has like credit counters. So let's go to page 122, right? Page 122. Okay, so this is page 122. 1 second. So this is credit-based flow control. Yeah, so page 122. So yeah, so 121. Okay, so yeah, credit-based flow control. Okay, long combination. Yeah, so like it shows here basic ideas, but it doesn't show Verilog code. So basically we created example with a Verilog code. So because basic idea is relatively straightforward. So but before you understand this basic idea, you need to understand why you need to do this at all. And basically what happens is that if you have some computation, let's go to Verilog Meetup. So yeah, like I put here actually on a main, like I said, main picture. So if you have some computation, some pipeline, and suppose some you can put check against. Suppose you have back pressure at the end of this pipeline, so the module cannot accept your data which is moving through the pipeline. So how can you tell to module on the left, which is upstream module, to stop sending you something? So one way of doing this is that you can put some ready signals in the middle and put everywhere ready signal and propagate this ready signal to the left. But if you do this in a like straightforward way, you will lower performance of your block, because and you really need to experience it, that because this means that once back pressure is gone, it will not start moving right away, but it will wait for like extra clock cycle and move only like after that. Now if you want it to move without such like slips, you need to implement a double buffer technique, which means that you let sync move and then stop. But if you do it in this way, you put a bunch of logic everywhere. So companies, this is the way what is advertised in this book, textbook used in Stanford, this one. However, this is how companies did around year 2000. Now they don't do it. They do something else. They do what this guy describes here. And so they put FIFO at the end of pipeline, and they say that we sync everything moving through pipeline into that FIFO. But now the question is how large that FIFO should be. So that FIFO should be able to accept everything what moves through your pipeline. Like if you suddenly stop. So everything which is flying through the pipeline, you should be able to move into that FIFO. Okay. But now the question is, at what moment sender should stop sending? And this is the tricky part. Initially, like many years ago, people were putting so-called almost full threshold in FIFO, because if you stop sending when FIFO is full, it's too late, because there are some transactions flying through the pipeline. They will come out and FIFO will be overflow. Okay. Now you can make FIFO of 2 times size of pipeline, but this is wasting FIFO. This is too large. So people were doing some schemes like FIFO almost full, but ultimately, unless you do something different, you have to make this FIFO 2 times larger than the pipeline. And the credit-based control scheme just means that in addition to FIFO, you also maintain credit, counting how many things are together in pipeline and in FIFO at the same time. And now you can put FIFO only of size of pipeline because you count some of them. And if nobody is going through pipeline and FIFO has space even for one element, you can still put transactions through the pipeline. Okay, but if FIFO is empty, but all pipeline has a transaction in every stage, you cannot put any new transaction even if FIFO is empty, because you know that all transactions currently flying will end up in FIFO. So credit-based credit counter is a simple way how to make things move every clock cycle back to back and not waste any extra flip-flops or like any extra memory. So this is like basic scheme, and this scheme is described in here, but it didn't go through university system. So modern students, unless they studied it by themselves, don't know it. And now the worst part is that this is only basic scheme, and there are many things on the top of the basic scheme. So by putting exercises, it's possible to like improve general awareness. Because what happened now is that students go to like electronic company, they don't know it, then they ask to implement something, or they ask to fix something in the existing code. They go to like a million lines of RTL and have no clue what is going on and why we have this extra counter there, what it's doing. And now they are asked to actually improve its efficiency. And now they have to go to some senior engineer or like architect who like go with them to whiteboard and explain how it works. And then like after 10 years, he will get enough experience to actually do this easily. So this is like not a very good overall thing. So it's better to put examples that train people at the start how to do this. This is kind of about microarchitecture. Yeah. So like any other questions about this?
So we are interested to go through the flow, right? I think you showed the synthesis and the timing, all of that. Are there examples to go through the entire flow?
Yeah, all examples go through the entire flow, including place value. So all examples is a rich GD. Yeah, let's go back to a terminal with the flow. So you can see in our terminal that we actually finished. So yeah, so
So
we
it
went
takes a
we
long
went through the whole flow. It takes a long time. So generally ASIC synthesis takes a long time. So basically we got bunch of reports here. Let me just show those reports on the screen. Yeah, so see in a run, so this is our main log. So you can see that when we do ASIC synthesis, first we run synthesis, then we run static timing analysis (STA) before we place things on the chip. Then we do initial floor planning. So floor plan is a coarse view of blocks, and here I have trivial floor plan. I just say that everything should fit into some rectangle of this size. Then it runs input-output placement, where to put pins. Then runs tap insertion, it's for debug. Then it does the power planning and inserts power wires. Then it does global placement, and then single corner static. So then do static timing analysis again after placement. Then it does detailed placement and another static timing analysis. Then it put clock tree synthesis. Then single corner, then static timing analysis again. Then placement resizer. So it found that some cells are too slow and want to resize some cells in order to fit timing. Then you does global routing, and it writes intermediate stages of Verilog. Then it does check for DRC violation, so design rule check, and checking wire length. So many stages, and finally at stage number 42, it does success. You see, but this is mostly job of physical design engineer. So for me as a logic designer, what is relevant is when a physical design engineer telling me that, like, Yuri, you don't fit into timing budget by like 80 picosecond, do something about it. And then I need to either massage some logic or to split this into different pipeline stage. So to put logic which was in one clock cycle, to do it in two clock cycles.
Sorry, which tool did you use for all of this?
Which
tool did you use for this?
This is called open lane. Yeah, this is ASIC. Yes, FPGA synthesis has its own things. Yeah, and we have it in the flow, so you can see report for FPGA. For FPGA, we use Altera Quartus, Xilinx Vivado, Govin IDE, then open source FPGA based tool, and like Lattice commercial tools. So all the standard tools like everybody uses. We are not trying to be fancy. We are trying to be only what people actually do on the job, because there are many like groups who are saying that like, let's design everything in Python using some strange way of design. I mean, like, this is great. It's just not how companies work in this way. And if you train person this way, he will not able to pass job interview. So we are trying to be as mainstream as possible. Like, yeah. Now, if you want, so now when you do this, it produces a bunch of intermediate Verilog representation. Like this is intermediate representation after synthesis. your Verilog becomes just a bunch of Skywater ASIC cells. You see, just many instances of cells. Some of them are empty. All those to connect cells together with each other. Yeah. Yeah, so those cells actually are here. So those cells are actually become true physical cells with silicon die. Yeah. Now, so this is the same thing after place and route. And so this is a final after like stage number. And then here is a static timing analysis report. So you see, so this shows that here is the worst parse. So you start from clock, you go through clock buffer, and then you go through different cells. And by following this, you can map it to your original code, which is kind of not trivial. Yeah, so you can map it. This is your original variable. So you need to see something is delaying in passing this variable. And then you go back to your code and see where the delay is. Okay, this is like a tricky part. And then it tells you that our clock period is 14. This clock uncertainty, clock external delay, and we have positive slack. So data required. So data arrival time is 350. So which is fine. So slack is mapped. So basically, what it's saying is that data, our like delay when we propagate through logic requires this number of a nanosecond in this case, and like it arrives enough so all like electric process became stabilized during certain time, and this time is less than the clock period. Yeah, so we have slack of 745, which is mapped. And now if this slack is negative, it means that your logic, you put too much logic in one clock cycle. And then you need to either split it or optimize it somehow. So this should be positive. Now, as a logic design engineer, sometimes this slack is slightly negative, but physical design engineers say, don't worry about it. If it's like marginally, if marginally doesn't fit, we can use our oven tricks in optimizing on physical level. Like in each case. Yeah, so this is like another report you are getting here. And then you have, yeah, so this then you have power report. This is the static power, so based on, actually, I don't know where it gets switching power in OpenLane, because it doesn't have this information. It's a weird number. But leakage power is power which is proportional to size, physical size. So basically, you have a certain size of cells, and it generates like it consumes, it leaks certain power. So this is power consumption. Yeah, this is a static power. Yeah. So finally, at end result, you get a file, and this is texture representation of such file where you have some layers of silicon and rectangles, so some rectangles in silicon. This goes to a foundry and it produces chip. So now, if you are doing the same thing with FPGA, then you're not getting GDS2 file. Instead, you're getting different report, which is similar but different. So this is a okay. So this is summary. This is timing report. So you also get STA, but this STA is different. So let's see. Yeah, here's a log. So you see, you are running Quartus Quarkus prime, you find something, produce a report, and it tells you like also slack, worst possible. So so you also have static timing analysis, and you also have fitting report, and it tells you here what is the logic utilization, a number of registers, a number of pins. So it tells you that you're using less than 1% of FPGA. So now, so what else can you do? Yeah, so you get a bunch of reports, and so where is the static timing? So project map summary. Yeah, here's STA summary. Yeah. So you can have static timing analysis for FPGA, and just like for ASIC, they should have critical path. Oh yeah, they have something here. Critical path. So they put some methods. So you can find critical paths from somewhere. I already forgot how to do it, but this is their like final report. So in their final report, they put slack, and then this is slack if you define that your clock is 50 megahertz clock. So then here's the slack. Opa, second. Yeah. Yes. Anyway, but this is something what kind of so how does it you feel that it like according to your like expectations? So is it something what you expect for your learning? So what is your yeah, okay. So just read to that thing, start to doing exercises. So like, are you using Windows or Linux? Okay. Just load that Icarus Verilog for Windows. Modify exercises, run script, and by doing this, you will go through and get that like textbook. And next week I will bring all different textbooks.
My takeaway is the lowest polar software that I need to install. The monitor with existing examples and maybe the most.
Yeah. So this is all in this post. Yeah, and send me your email. I will put you to the list to the Google group, so you will get messages. Yeah. So you or you can send email to this website, which is like link for Verilog Meetup. But it's better to send it directly to me because I am looking here not every time. Yeah. So you just follow what is on.
You already had also digital designs
Oh, but is it a new edition or old edition? Because this has multiple edition. Yeah. Okay. So see you. Yeah. So basically, you can just follow instruction here.
So this website has a list of tools to install.
Yes. So you just list of tools. For list of tools, I will send. There is a presentation. But basically, if you get a repository and if you run example, if something is not installed, it will tell you what is to install. Yeah. So you just get repository run. It says, oh, you don't have this thing installed. Then you install it. Or alternative. Oh, I totally forgot this. But alternatively, I have a bootable SSD with Linux, which have everything installed. So I can give you one of those SSDs. So what you do with this SSD? So let me show you how it works.
When they get the bootable SSD, you have all the formats shown in there. When they submit it won't be in their phone repository. It will go to the main server.
Oh, but they cannot submit to the main branch.
So they need to, so when I do my homework, I don't use bootable SSD for this reason, because it already has a clone of.
Yeah, this has clone, but you should have a permission to push it, password to push it.
Push it in when so the clone is. So it's a clone.
Yeah, if you try to push it into this repository, it will prevent you from doing so. But you need to create clone of the repository and make it private. Or you can just send me. You can just zip it and send it to me as a zip, which is kind of the easiest solution. So let me just show you. So I can show you on your computer. So do you have a computer with you? Yeah, I can show. I can just give you SSD and just show you how to use it. Yeah, but I can give you this SSD. So this one, but what kind of computer is it? Windows or Windows. Yeah? Okay. So now what you need to do is that you first you go to. First you go to Windows setup. So some computers you can just boot it right away, but for some computers, let me show you. So, oh, this is Dell. Yeah. So go to start. Go to start, and now go to settings. Yeah, go to settings. Go here, restart. Yeah, change advanced startup options here. Okay, press restart now. Restart now. Okay, so now let's see whether it works. But huh? No, don't go to it anyway. Just wait until it starts. Yeah, do not touch anything. Yeah. So this one has all FPGA tools like Altera and Gorin, but not Xilinx. No. Yeah, for Xilinx you need larger thing. Yeah.
You have anything for lattice?
I'm looking for somebody who can. I mean, we have for lattice, but thing for lattice was put by a guy in Tyumeny in the middle of Siberia, who put it for lattice, and then he told me that I'm not writing code in the right way, and the architect didn't finally says that he doesn't want to be part of the project because I'm a good guy, but he thinks that it should be written in a different way. So now we are looking for somebody who can actually do this for lattice, or eventually I will do it by. Okay, here.
I have some lattice board, but I don't even
So
know.
you put here usage device. Oh, wait a second. On board, no, it's not right. Continue. Oh. One second. No. You can do it. You can do it by default.
No, that's also
Not working?
Okay, let's see. Status settings. Status settings. Startup repair. 1 second.
like Xilinx they have their own software.
Wait.
Anybody use it? Like
How to? Let's actually exit. Okay, let's start again. Use a device, but it does not allow. Okay, maybe we need to connect it to different USB port. Okay, so
There's one here.
Okay, let's connect it. Yeah, but it doesn't show anything in here. So and void nick. Maybe it does not allow. Okay, what if we simply turn it off? What? Okay, let's simply turn everything off. And let's just try turn it off and then turn it on. And let's just try like F2. Sometimes it just works in this way, or like escape button. So can you? If it goes to the startup menu, much easier. Boot. Oh yes, UEFI boot. Oh, file browser boot Windows boot. Okay. So for some reason doesn't want to boot UEFI. Firmware advanced USB emulation function. Do you have secure boot? Secure boot system date. I forgot how to. Okay.
The secure boot is here.
Yeah, here. So let's turn off secure boot and see what happens. Secure boot and log. Secure boot status enable. Secure boot enable. So let's actually disable secure boot. Okay, then we can change it. And then we can do. Okay, so what's the F10? So can you? Yeah, no, I mean this particular one, this small chip. Let's see. So let's press F2 again. Okay, let's see. Nope. Okay, yeah, here I need another person who is Alex Belets who can do it. He can do it for any USB emulation. Maybe we should put USB emulation disabled. Actually, you know what? If you turn off secure boot, let's actually start with that. Restart again. Now they have hyperscale plus. Five boot. Why it's not booting? Okay, so we turn off secure boot. So let's just try the same thing what we did before. Now, like I'm not sure, but if it doesn't, it doesn't want to boot. You have BitLocker.
Yeah.
Yeah, with BitLocker it's not going to work. Yeah.
Something you installed?
No, it came with this.
Okay, BitLock.
Yeah, with a BitLocker you need to remove BitLocker. Okay, so you're working this way. We need to restore secure boot back. Yeah, I remember. Okay, let's do. Let's in this case put back secure boot. Yeah, so somehow I have a guy Beres who knows how to do this, and he solved such problem for me. I had this as well. Yeah, so let's put secure boot back. And they have also okay, so let's do save and exit F10.
So just the reset doesn't work. You need to like completely power cycle your computer. That's That's how it worked for me. So whenever I just reset it, or put it into sleep and call it back, it wasn't working. Had to completely turn off. I think.
But did you use BitLocker or what was? Did you use it with a BitLocker? I know that with BitLocker it doesn't work for sure. Okay. Okay. Let's do last attempt. Let's try to do this restart again. Yeah, with BitLocker it doesn't. If you want, I can loan you one of my like computers I have for this reason, because I have several like you know.
It's problems and it's, I guess, they are trying to identify better way to have a separate business.
I have some like computers like this one. It's like old computer, and I can load it. But let me just make sure that it has everything on it.
I'm doing digital stuff.
Okay.
As a freelancer, a contractor, or working for a company?
Yeah, but like unless you have a PG board right now, you actually don't need anything, because you can just install. Because yeah, so like I was showing how to, yeah, let's see it. Let's try to do it. This one is better. Okay, this one.
New customer support. So
Oh.
You go for all the open lane.
Okay, so this we can stop. Okay, so this is done.